Today is Sunday, August 7th, 2022. It is also day 385 of data science, and today I have time to kind of go through all this, so I'm going to do that. So I'm going to do an area between 2 points problem from Khan Academy. I'm going to do it using Python, using the TI-83 and the TI-84, and I'll do it using z-scores, right? So the College Board way. So let's get started. So a set of statistics exam scores are normally distributed with a mean of 76.55 points and a standard deviation of 5 points. What proportion of exam scores are between 79 and 86.05 points? Now, this is a little bit more, it's not harder or complicated at all. It's just one more step in Python, but it's super easy with the calculator. So in Python, if I have a normal distributed problem, then I know that I'm going to need the normal CDF function. So I have to import that from scipy.stats. So norm, and then I'll do norm.cdf, and CDF stands for cumulative density function. So it basically calculates the cumulative density up until a certain point x, and that's going to end up being 79 for me. And then the loc is going to end up being 76.5 because the loc is the mean, and then the scale is the standard deviation, and that is 5 points. Now here's what this line of code does. This over here is the proportion of exam scores that are lower than 79, and then what we really want is the proportion or the area between 79 and 86.05. So in Python, there's only this function CDF specifically, and there's also the SF function, which is basically calculating the area to the right. So that would look like norm.sf, and then I'll put in my x 86.05, have the loc be the same, 76.55, and the scale be 5. And what this does, it's the area or the proportion of exam scores that are higher than 86.05. So if I know that the total area is 1, right, then all I have to do is add these two together and subtract that value from 1, and then I get the area in between the 2 points. And so this is the area to the left, and this is the area to the right. And this over here is the total area, which is equal to 1. And then the area between the 2 points, I guess, is going to be equal to the, it's equal to the total area minus the area to the left plus the area to the right. And I run that. Let's see, what's the issue? Name total area is not defined. Did I not say, oh, it's tota. Let me change that to total. All right, and then I can go ahead and round the area between the 2 points by 4 decimal places because that is what it asked for. Copy that and then put that in here and check if I'm right, and I am. All right, so now I'm going to plot the graph to give you a visual of what I just did, and then I'm going to do the TI-83 and TI-84 stuff. Alright, so for plotting, I'm going to need matplotlib because it's a plotting library, so I'll do matplotlib pyplot as plt. And I'll also import numpy, and that's just going to help me plot my x values. So when plotting, I need my x values and my y values. And my x values are basically going to be generated by this linspace function. And this linspace function takes in 3 points. So it takes in your starting point, your endpoint, and then the number of points in between. So I kind of go, in respects to my standard deviation, I actually go like 3 times the standard deviation. So let me see, I would do the mean. So actually, maybe I'll just do the mean, make it a variable and call it 76.55. And I'll do the standard deviation and set that equal to 5. And so over here, I'll just set that to the mean minus 3 times the standard deviation. And then over here, the ending point would be the mean plus 3 times the standard deviation. And then I want 1,000 values in between. And then for the y values, I'm going to do norm norm.pdf, and this is the probability density function. And what this does, it calculates the probability density at a certain point x. And so in this case, I want the values that it calculates to be all of my x values with the given mean and standard deviation. Now if I run that, nothing happens because I haven't plotted it anything. So I'll just do plt.plot, and I'll just plot in my x values, and I'll plot my y values. And now I'll be able to see a normally distributed graph like that. So pretty, isn't it? All right, so now this part I wanted to explain. This is basically where it starts, right? So it starts 3 times, like from the mean 3 times the standard deviation, so to the left. So that's why it starts kind of over here. If the mean is 76.55, it's going to be in the middle. So you can see 75 kind of in the middle, 76.55 is in the middle. And then so it's the starting point is over here, 3 times to the left of the standard deviation, or from the mean. And then, and then the ending point is the mean, right? From the mean 3 times the standard deviation, and then 1,000 values in between. And then PDF is calculating the probability density, which is a specific density, right, of each of the x values in accordance with the mean and the standard deviation. Now, I like to do a title, so I'll do PLT title and set this equal to normal distribution of exam scores, with the mu and the sigma being their respective values. So let me just get the symbol over here. So the mu symbol, go back to my data science. So mu is equal to, what is it equal to again? 76.5, 55, and the sigma symbol, that's not how you spell symbol in statistics, is this over here. Let me X out of that, go over here and set that equal to, I honestly could just set that equal to the value over here. What do I call it? The standard deviation. Oops. As a string. Beautiful. And then let's see. Width, and then maybe I can just do, actually, normally do the scam scores, and then it's just another way of writing it. Okay, let me just end that there, and then I'll also give it a y label, and I'll set this equal to density or proportion, and then I'll also give it an x label, and this is going to be exam scores or scores. All right. And that's my graph. So I'm just going to go ahead and save that. I don't actually have to save it. I could just copy image and then go to my whiteboard. And this is where I'm going to paste it. And I'm going to work on basically explaining what I did in Python. So I will lock that. All right. So let me get my pen out. So basically what I did here is they basically wanted the area in between 2 points. And so if I remember correctly, let me just put this to the side over here. All right, so they wanted, let me put this one to the side. All right, so they wanted 79 and 86.05. So 79 is right about here. Why am I not able to write on it? Oops. All right, 79. Oh, it was frozen. Let me move that to 2 or 1 or something. All right, so 79 is literally like right here. So that's 79. And then let's see, 86.05 is like right about here. So that's 86.05. And so this is the area basically that they wanted. They wanted the area under this curve. That is the proportion of exam scores in between those 2 points, right? That's what they wanted. And in Python, there is no, I believe from my knowledge, there's no way so far that I know to get that area automatically. So I actually have to find the area to the left of 79, and then I have to find the area to the right of 79, add those two areas together and subtract it from the whole to get this pink part, right, which is the area in between, if that makes sense. So essentially what I had to do in order to get, in order to get the area in between, that is not how you spell between. I can't even spell. Hold up. Let me put this as a 2. Alright. Between the 2 points, area between points, I have to add the area to the left of 79, which I'm going to give another color like yellow. So that's all of this over here. Right, so I have to add that. So this is area to the left. And I have to add that to the area to the right of 86.05. So that should be this area over here. And then I have to add those, right? And so that's the external area, and then I have to subtract that from the total area, which in this case is literally the whole normal distribution in itself. So that would literally just be, you know, the entire graph. So like, that would be the entire graph. So it's just basically, you know, trying to get this part over here. So that's what I did in Python. That's literally all I did. And I just used, you know, norm, CDF for this one and SF for this one, because norm CDF calculates the probability, I'm sorry, not the probability, the proportion to the left, and SF is the opposite of CDF. It's 1 minus CDF actually. It calculates the proportion to the right, and so that's what that does. And then I just subtracted that from the total area, which is the total, right, to get the pink part over here. So that's that. So that's what I did in Python. Now, let me see. Oops. So this is with Python, and now I'll do it with the TI-83. So for the TI-83, alright, so for the TI-83, in the calculator, you go to get the function, you go to second vars, and you select 2. And it's going to be the normal CDF function, and it's going to literally look like this. That's all you're getting, and you have to know which values to put in there. So the values that I like to call it are lower bound, upper bound, mu, which is your mean, and sigma, which is your standard deviation. Now your lower bound is basically these 2 points are the interval in which you want to find the area under. So remember, like in math class, the teacher had a graph and you had to find like the domain of the graph. So basically where it starts and where it ends. So it could start at -3 and 3. And so the interval would be -3 and 3. If it didn't continue. So that would be the interval, right? The interval in which the graph is present. So kind of the same idea in normal CDF. Lower bound and upper bound are your intervals in which you want to find the area, right, inside those, or like between those 2 points. And so that's easy in this case because they're giving us those values. So the lower bound would be 79, and then the upper bound would be 86.05, and then obviously the mean is 76.55, and the standard deviation sigma is 5. And so now all you have to do is click enter, and it gives you your answer, right, of 0.2, what was it, 0.2, 0.2834. You would just have to round it. Obviously it's going to give you like a longer answer, but she'll round it to that 4 decimal places. And that's it for the TI-83. And then for the TI-84, the only difference is the format. So it's the same thing. You go to second vars, and then you go to 2, and you select your normal CDF function. And what that's going to do, it's going to give you a window, or like a list of values. And then it's going to look like this. So it's first going to ask you for your lower value, your upper value, your mu, and then it's going to ask you for your sigma, and then there's going to be like a paste word down here. So again, your lower is 79 because that's the value you're starting with. Your upper value when you're stopping is 86.05. Your mu is 76.55 and your sigma is 5, and then you hover over the paste and it turns black, and then you just click enter, and then it gives you your answer of 0.2834. And that's that. All right, and then for the z-score method, z-scores, you would have to use the standard normal distribution instead of the normal distribution. And z-scores is basically just converting the 2 points to be z-scores. And so the formula for that is just your point minus the mu divided by the mean. So for the first point, it would end up being 79 minus 70, what was it again? 76.55 divided by 5. And then for the second point, it would end up being, let's see, 80 minus 76. It was 80.6. I don't even remember. 86 point, whoops. Let me change that. 86.05 minus 76.55. Divide that by 5. And let me do the math real quick. All right, so for the first one, it's actually 0.49. And then for the second one, it's 1.9. So basically, this over here, this little point over here, is the equivalent to this, but in z-score. And then this point over here is the equivalent to this, but in z-scores, right? And so now to do this with the TI-83 and TI-84, you would have to use a standard normal distribution, and that means that the mean would have to be 0, and the sigma would have to be 1. So in order to do that, I'll actually plot it over here. It's literally the exact same thing, except that literally it's just the mean is 0 and the standard deviation is 1. So this would be changed to 0, and this would be changed to 1 if this thing loads. I'll just change this to be 1 over here for easy stuff. Call it the standard normal distribution, and then obviously change it over here to be 0 and 1. That's 70, not 0. And now this is literally it. So I'll go ahead and copy that image, and that's literally the graph that I'm going to be using to solve this problem here. So I'm going to paste that, and I'm just going to move that over here, move that over here, probably move it on top over here, it doesn't even matter anymore, and just kind of lock it. All right, so in this case, for the TI-83, it's the same thing. I'm not even going to write it again. I'm just going to do it in a different color. So for z-scores, whoops. For the TI-83, let me see. So for TI-83, it would end up just being 0.49 to 1.9 and then 0.1, and then click enter, and it would give you the same answer, 0.2834. And then for the TI-84, it would just literally be 0.49 for the lower, upper would be 1.9, mu would be 0, sigma would be 4. Click enter, and you'll get the same answer, 0.2834. And then that's literally the exact same thing. So if you were to place the graphs, the two graphs on top of each other, they are the exact same thing. It's just that the points, are different. Even over here, 0.79 is right here. Right? Not 0.79. What is it again? 0.49? That's somewhere over here. Like 0.49. And then the other one was 1.9, which is about like over here. And so that's the same area, literally in like red in between those 2 points. That's the same area just as it was in the normal distribution. And it's the same idea. Whoops, that's like really bad. I feel like color coding always makes it easier for me to understand things when I can visually see stuff. Even though I'm not doing a really good job at doing this. Anyway, so this is the standard normal distribution, and I'll go ahead and do this with z-scores. So this is the standard normal,